Welcome. This is going to be a introduction to acids and bases. Acids and bases are a special type of compound that we use in chemistry, and it's quite common. So, one of the first people to kind of propose what an acid and a base is a Swedish scientist by the name of Savant Arrhenius. He was one of the first people to propose a definition, and of course, he wants to be remembered forever. He called an Arrhenius acid. Whoops. An Arrhenius acid is a compound that produces hydrogen ions in solution. So, Arrhenius acid produces H ions. An Arrhenius base produces hydroxide ions in solution. So, for the most part, from what he studied, it works for just about most acids, but not all. There are a few exceptions, and there is a broader definition, which we'll get to later. So, to kind of give you a visual, HCl solid form is just called a hydrogen chloride. The minute we put this into water, it becomes an acid. And what makes it an acid is that it breaks apart into ions. And for hydrochloric acid, it breaks completely into ions. So this would be the definition of an Arrhenius acid. It produces hydrogen ions in solution. The opposite holds true for sodium hydroxide, very strong base. We put that in water, it becomes a strong base, and it completely breaks into ions in solution. So this would be considered an Arrhenius base because it produces hydroxide ions in solution, and you can see in the compound itself that it's got hydroxide ions. Okay, where Arrhenius definition fails is ammonia. Ammonia is NH3. Problems here. Now you would think that this is going to, and hydrogen is going to break apart to form NH2 and a hydrogen ion, but it doesn't. It's a big no-no. What ammonia does do is that it actually will, well, don't forget that there is water in here. It's going to strip off the H off that water to form ammonia ion. And since it's stripped off the H off the water, water is going to leave behind is hydroxide ion. So this compound does not produce hydrogen ions in solution. It made a hydroxide ion solution because it used water to do so. And this would not follow suit with the Arrhenius acid or base because of it. So, and this is one of the exceptions to his definitions. So a group of gentlemen realized this, and they came up with their own definition that's a little more in general. And it's called the Bronstein Lowry definition, named after Johannes Bronstein and Thomas Lowry. And according to their definition, an acid is a proton donor. And when we say proton donor, that's really a hydrogen ion. And a base is a proton acceptor, so anything that accepts a proton. Okay, according to their definition, acids and bases always comes in pairs. So for example, when we put acid in water, or HCl, hydrochloric acid, we would call this my acid, and there always has to be an acid-base pair. So in this case, water is going to act like a base. It can also act like an acid in other situations, but for this one, it's acting like a base. Because what happens is, this hydrogen will go with the water to form a hydronium ion, and then chlorine will be by itself. So in this case, HCl is a Bronstein Lowry acid, and water is a Bronstein Lowry base. These guys do have names here for what's left over. So for this chlorine that's left over, we call this a conjugate. And it's called a conjugate base. So that's what's left over after the hydrogen left. The substance that received the hydrogen after is called a conjugate acid. So in Bronstein Lowry acid and base, every single one has a name for it. Acid, base, conjugate acid, conjugate base. And so you have to be able to label all four. Okay, the difference between a strong acid and a strong acid and a weak acid is that strong acids dissociate completely into ions. It means they break apart 100%, close to 100%. Weak acids partially dissociate into ions. So for example, again, HCl, when we put this into water, you're going to get 100% dissociation. So what you're going to have in solution is this, and then water, just it is in water. But this is practically 100% breaks apart. That's what makes it a strong acid. A weak acid such as HF does not break apart 100%. It will leave a little bit of hydrogens, it will leave some fluorine ions, but you're still going to have HF in solution, as well as that water that's still floating around. So this is not going to be 100%. It'll vary between 0% to 95%, something like that. The fact is, this does not break apart. There will still be left in solution. Now, how do you know what's a weak acid and a strong acid? You have to memorize just the strong acids, because there's not that many, and strong bases. So for example here, there's only 1, 2, 3, 4, 7, 6, well it's even less. 6 strong acids you have to memorize. And there is some patterns here. So HBr, HI, and HCl, those are my halogens. So those are kind of easy to remember. And the ones you have to know, nitric acid, sulfuric acid, and perchloric acid, you have to memorize those 6. For strong bases, there is patterns, and I wrote it like this for a reason. So lithium, sodium, potassium, rubidium, cesium, if you notice, they're all group 1A alkali metals. So when they're paired up with hydroxide, they're strong bases. And the group 2A alkaline earth metals, these 4, when they're paired up with hydroxide, they will form strong bases. So you need to memorize these, because there's only a few strong acids and strong bases to remember, but there are thousands of weak acids and weak bases. So it's easier to remember the strong ones. And when you've never seen it before, just assume it's a weak acid or weak base. Okay, so let's do some examples. So in this problem, I want to write a balanced molecular formula, complete ionic equation, and a net ionic equation for when you react HCl with NaOH. We also want to identify the acids and base, the acid, the base, the conjugate acid, and the conjugate base. Okay, so for the first part of the question, we should know how to do these pretty proficiently, since this should be review. So this is going to form water, HOH, that's going to be a liquid, plus NaCl, and NaCl soluble, we write that is aqueous. So that is my balanced molecular equation. It's a pretty easy one to balance. There's no coefficients, just all 1. My complete ionic is when you break every single one of them into ion except for the liquids and solids. So H plus Na positive plus OH minus. So those all break into ions. Water still stays together. It is a liquid. But sodium and chloride comes back as ions. So that is my complete ionic equation. The net ionic is whatever produces the solid or liquid. So hydrogen ion plus hydroxide ion forms water. Exciting stuff. Okay, some things of note. When you mix a strong acid with a strong base, if you notice, all it does form is salty water. So usually when you mix a strong acid with a strong base, it forms a salt with water. Okay, the next part was to identify the conjugate acid and the conjugate base. Oops. Okay, so after it's balanced, now conjugate acid is a proton donor. This is donating a proton. This is going to be my base. So since the H goes with the OH and the OH received it, that's going to be my conjugate base. And this is going to be my conjugate acid. Whoops, sorry. Flip that around. This is going to be my conjugate acid, and this is going to be my conjugate base. So the conjugate base is what's left over after the H left. Normally, and it seems kind of weird to put that sodium there for me, but normally when we do acids and bases, sodium is soluble on both sides, so we normally don't include those when we're looking at that. So anyways, in this example, the conjugate base would be really the Cl ion. Okay, another problem with an example is to write the dissociation for these compounds. Well, what this really means is, what does this look like when you break them down into its ions? So HCl will form an hydrogen ion plus a chlorine ion, so that's it. Acetic acid is HC2H3O2. So when that breaks apart, it's just hydrogen ion plus the acetate ion. Remember your polyatomic ions. Okay, so those first two are pretty easy. Now we're getting to a little more tricky ones. Here we have an ammonium ion. Okay, what is that going to break apart into? Well, this is going to break apart into NH3 positive plus, oops, not NH3 positive, erase that. H positive plus NH3, there's no charge on that NH3. Okay, the aniline ion is a little tricky one, and these are ones you just have to kind of start observing it and being exposed to it. This is going to break apart to C6H5 NH3 positive. This is going to break apart into C6H5 NH2 plus a hydrogen ion. So if you notice here, the 3 left is becoming 2 and the hydrogen breaks off. So it's similar to the ammonium ion. Again, this will be an exception to the Arrhenius acid and base. Okay, for the next one is pretty tricky. So this looks kind of weird. This called a hydrated aluminum 3 ion. So what this breaks apart into is, so aluminum, let me write this out first, H2O, 6 of those, but the whole thing has a +3 charge. This is going to break down into, it's still going to be aluminum, H2O, but only 5 of them. One of the waters will actually break off. You'll have the hydroxide ion left over. The whole thing will have a +2 charge now, and then you still have a hydrogen ion, so it is considered an acid. But if you notice here, I originally had 6 waters to begin with. One of the waters will break off in H. It'll leave 5 waters behind. The OH is still in the brackets, and that hydrogen kind of takes off. And then the whole total charge for the aluminum hydrate ion now is a +2 charge. This one you will need to commit to memory. It is kind of a tough one. It's never seen this before, but this is where you're being exposed to it, so please remember it. Alright, so I hope these examples and this introduction to acids and bases helps.